Welcome back to this series on neural network programming. In this video, we will look at a practical example that demonstrates the use of the tensor concepts rank, axes, and shape. To do it, we'll consider a tensor input to a convolutional neural network. Without further ado, let's get started. In this neural network programming series, we are working our way up to building a convolutional neural network. So let's look at a tensor input for a CNN. In the last two videos, we introduced tensors and the fundamental tensor attributes, rank, axes, and shape. If you haven't seen those yet, I highly recommend you check them out. What I want to do now is put the concepts of rank, axes, and shape to use with a practical example. To do this, we'll consider an image input as a tensor to a CNN. Remember that the shape of a tensor encodes all of the relevant information about a tensor's axes, rank, and indices. So we'll consider the shape in our example, and this will enable us to work out the other values. The shape of a CNN input typically has a length of 4. This means that we have a rank 4 tensor with 4 axes. Each index in a tensor's shape represents a specific axis, and the value at each index gives us the length of this corresponding axis. To break this down, let's work backwards, considering the axes from right to left. Remember, the last axis, which is where we'll be starting, is where the actual numbers or data values are located within the tensor. If we are running along the last axis and we stop to inspect an element there, we will be looking at a number. If we are running along any other axis, the elements there will be multi-dimensional arrays. For images, the raw data comes in the form of pixels that are represented by a number and laid out using 2 dimensions, height and width. To represent 2 dimensions, we need 2 axes. So the image height and width are represented on the last 2 axes. Possible values here are 28 by 28, as will be the case for our image data in the Fashion MNIST dataset, or as another example, 224 by 224, which is the image size that is used by the VGG16 neural network, or really any other image dimensions we can imagine. The next axis represents the color channels. Typical values here are 3 for RGB images, or 1 if we are working with grayscale images. The color channel interpretation only applies to the input tensor though. As we will reveal in a moment, the interpretation of this axis changes after the tensor passes through a convolutional layer. Up to this point, using the last 3 axes, we have represented a complete image as a tensor. We have the color channels and the height and width, all laid out in tensor form using 3 axes. In terms of accessing data at this point, we need 3 indices. We choose a color channel, then we choose a height, and then we choose a width to arrive at a specific pixel value. This brings us to the first axis of the 4, which represents the batch size. In neural networks, we usually work with batches of samples opposed to single samples. So the length of this axis tells us how many samples are in our batch. This allows us to see that an entire batch of images is represented using a single rank 4 tensor. Suppose we have the following shape for a given tensor, 3 by 1 by 28 by 28. Using the shape, we can determine that we have a batch of 3 images. Each image has a single color channel, and the image height and width are 28 by 28 respectively. This gives us a rank 4 tensor that will ultimately flow through our convolutional neural network. Given a tensor of images like this, we can navigate to a specific pixel in a specific color channel of a specific image in the batch using 4 indices. Let's look now at how the interpretation of the color channel axis changes after the tensor is transformed by a convolutional layer. Suppose we have a tensor that contains data from a single 28 by 28 grayscale image. This gives us the following tensor shape, 1 by 1 by 28 by 28. Now suppose this image is passed to our CNN and passes through the first convolutional layer. When this happens, the shape of our tensor and the underlying data will be changed by the convolution operation. The convolution changes the height and width dimensions as well as the number of color channels. The number of channels changes based on the number of filters being used in the layer. Suppose that we have 3 convolutional filters. And let's just see what happens to the color channel axis. Since we have 3 convolutional filters, we will have 3 channel outputs from the convolutional layer. These channels are the outputs from the convolutional layer, hence the name output channels, opposed to color channels. Each of the 3 filters convolves the original single input channel, producing 3 output channels. The output channels are still comprised of pixels, but the pixel values have been modified by the convolution operation. Depending on the size of the filter, the height and width dimensions of the output will also change, but we'll leave those details for a future post. With the output channels, we no longer have color channels, but we have what we can think of as modified color channels, and we call these channels feature maps. These so-called feature maps are the outputs of the convolutions that take place using the input color channels and the convolutional filters. So we combine an input color channel with a convolutional filter, we do a convolution operation, and we get a resulting output channel that we call a feature map. The word feature is used because the output represents particular features from the image, like edges, for example. And these mappings emerge as the network learns during the training process. We should now have a good understanding of the overall shape of an input tensor to a CNN, and how the concepts of rank, axes, and shape apply to this understanding. We'll deepen our understanding of these concepts in the future videos when we begin building our CNN. Don't forget to check out the blog post for this video on DEEPLIZARD.com and check out the DEEPLIZARD HiveMind for exclusive perks and rewards. I'll see you in the next one.
In 2012, a young researcher named Alex Krizhevsky, working under Geoffrey Hinton in the University of Toronto in the AI laboratory, designed a piece of software that was able to learn visual recognition by itself. It was able to learn visual recognition by learning from a large amount of data using a technology, using an algorithm called deep learning. In 2012, he designed the AlexNet. And he submitted AlexNet to the global competition of large-scale computer vision recognition competition. And in 2012, when he submitted AlexNet to that competition, he won. AlexNet beat every single computer vision algorithm that was developed by experts, computer vision experts, who hand-coded mathematics, hand-coded algorithms, specifically for visual recognition. Without specific training in computer vision, Alex Krizhevsky's AlexNet, trained with data, performed on 2 GTX 580s from NVIDIA, and he won the competition. He beat everyone. He beat every single computer vision algorithm that had been developed up to that point. The results of AlexNet, his achievements, caught the attention of every computer vision scientist, every artificial intelligence scientist around the world. AlexNet, 2012, Alex Krizhevsky started the GPU deep learning revolution. It was the big bang of modern AI.